matematica.
Anziché fisica matematica, sì.
Okay, welcome to our weekly group seminar. So this week we have the pleasure of having a speaker, Andris Erglis, who is a new entry in our group. Andris completed his bachelor in Latvia. He's from Latvia, as you know, and then he made his master in Saudi Arabia, and then he moved to Germany for doing his PhD, supervised by Stefan Buhmann, between University of Freiburg and University of Bonn. And his outstanding expertise is on Bose-Einstein condensation of photons. It's a bit different from the topics we deal with in this group. And today I think he will actually speak about that, in particular driven-dissipative dynamics of the photon Bose-Einstein condensate. Please.
Okay, thank you for the introduction. I'm happy that you're here. Yes, so the title, as you see, is quite long, and there are two parts which I will tackle. So, namely, first, I will talk what is photon Bose-Einstein condensate in general, and then I will give some results of the experiment which I did in Bonn regarding the driven-dissipative dynamics of the condensate. Now, the experiment I actually did was with another guy, Alexander Sajid, and it's experimentally very nice to be doing it two people together, because sometimes you need to measure at 2 o'clock at night, and if you have two people, then it's much easier. And yes, so yeah, these are the thought theory and experiment both together. Now, maybe a bit of introduction about the Bose-Einstein condensate from historical perspective is that 100 years ago, exactly 100 years ago, this condensate was predicted by two physicists, Bose and Einstein. And Bose initially described photons purely from statistical properties. He sent his results to Einstein, and Einstein was very impressed by Bose's work, and he developed the theory further, and he predicted a new state of matter, and which we now call a Bose-Einstein condensate. Now, 70 years later, experimentally, the first atom BC was created with rubidium or lithium or sodium atoms. And it was so late because it was very hard to create this state, because you need to have very, very low temperatures for atoms, so order of nanokelvins. And this was a very big discovery. This was also awarded a Nobel Prize 6 years later. And people were even dubbing it in media as a fifth state of matter, besides the ones which we know already. And then, finally, in 2010, the first photon BC was created in the same group where I was doing the experiment, in group of Martin White. And here in the picture that you see this small dot, this is a photon Bose-Einstein condensate. Now, my talk will consist of two parts mostly. One will be the introduction of what is a photon BC, and then I will go to the project which I was doing, namely driven photon BC, and I will give you introduction of theory, experiment, and then I will also talk about some of the results which we obtained. So, in one sentence, photon BC can be defined as a special state of light where photons are in thermal equilibrium, and they all occupy the ground state of the system. Or not maybe all of them, but there is a macroscopic occupation of the ground state. And for starters, without even going into details, let me just show you a spectra of photons, so you see that they that the spectra obeys the Bose-Einstein distribution. And what you see here is on x-axis is the wavelength, on y-axis is the photon number in some arbitrary units, and here you see the photon spectrum, and here 570 nanometers is the ground mode of the system, and the lighter green part is where there is no occupation at this wavelength. But what is true here is that the distribution, spectral distribution of photons, is fitted with the Boltzmann distribution corresponding to 300 Kelvin temperature, which indicates that the photons are in thermal equilibrium because they can be described by Boltzmann distribution. And this is in log scale, that's why this slope is linear. Now, so this is one of the conditions, thermal equilibrium is satisfied. Now, this is below some threshold. This is just a thermalized photon gas in the system. If we now go above some critical threshold, in this case, the critical photon number in the system, if we go above that, the excited states are saturated, and all the excessive photons which enter the system, they now go into the ground mode. So this is for smaller photon number, and this is for even bigger photon number. And this is macroscopically occupied ground mode. And this is satisfied. And now this spectrum, for example here, this then corresponds to a spectrum of a photon Bose-Einstein condensate. Now it's interesting also to look what happens in space. So these are just two pictures which we took in the lab from the camera. So this is real colored pictures. So this is below the threshold when we just have thermalized photon gas. And this is above threshold where we have now a macroscopic occupation of the ground mode. And specifically in this case, it's the PEM00 mode of the cavity. And how the other excited states look like, also took some pictures of those. For example, this is the second excited mode, this is the third, this is the fifth. I mean, arrows don't really correspond to those wavelengths. Just schematically, I'm showing this. And as you see, these are just Hermite-Gaussian modes of the cavity. Now, I think now it's time to start maybe talking about how to achieve this condensate, what we need to have. This is why I'm writing like a recipe. What ingredients are necessary to achieve this state of light? So first of all, we need to create effective mass for photons. Then what we need to have is a thermalization mechanism of photons, because photons by themselves, they don't thermalize, they don't interact with each other. Third, we need to have low system losses. So photons are thermalized before they leave the system. And the final part is we need to achieve a steady state, because if photons are not at a steady state, there is also no thermalization. Now, the first condition we can achieve by introducing a cavity, which introduces the trapping of photons. And so if the cavity has this length, it has this wave number kz, and it's fixed. We fix the length, which means that we can assign with this energy for photons, we can define a photon mass and photon, which corresponds to the cutoff frequency of this cavity. So cutoff frequency is just the minimal frequency of the cavity in the longitudinal mode. And here, for example, what you see is the diagram of the photon energy as a function of transversal wave number. So transversal wave number is along the mirrors, which we change. Now for free photons, this is the dashed line. This is basically an untrapped photon gas. It's like a black body radiation. And here, with this trapping, we introduce non-zero energy for zero transversal wave number. And the zero transversal wave number is the ground state of our system. Also, I need to mention that this energy is much higher than kBT, so no thermal photons can be excited at this energy. which essentially means that we are disentangling the problem of black body radiation. Now, secondly, for the thermalization mechanism, we introduce dye molecules, which introduce effective photon-photon interaction via multiple absorption emission processes. For example, here I show some cavity modes, and the molecule can emit photon in the cavity mode, and it also can absorb the photon from another cavity mode, for example. And molecules can also spontaneously emit a photon. Now, also low system losses means that we introduce highly reflective mirrors, which reduces the leakage. And I think this is one of the problems why photon condensate was reached so late, because the problem was to find mirrors which reflect very well. And finally, since we already have natural losses in the system, like leakage on spontaneous emission, to reach a steady state, we need to externally pump the photons inside the cavity. And yes. Yeah?
What are you doing to spraying this
Sorry?
This dye like something you spray into
It's like a liquid solution in the cavity. We put a drop of liquid solution. Yeah, I will show you later in the experiment. Yes. Now, for example, if one condition is removed, let's say if we now have a very leaky mirror, we get a laser. So sometimes people wonder what's the difference between photon condensate and laser. So this is the difference. When we have large losses, then we have a laser. I mean, this is not only a condition. We could also achieve laser-like structure by tuning absorption emission coefficients of the molecules, but this is the simplest case scenario. And now maybe I can talk about this critical threshold, before which I mentioned was the critical photon number. So how we control the critical photon number in the cavity, if we are below or above, we just change the pump strength. So increasing the pump strength, we can overcome the critical photon number and we can achieve the condensate. Okay, maybe now I can give a bit of some equations, which are very simple. And here I'm just now leaving all other excited modes away. I'm just considering a single mode, the cavity, which is, I assume this is the ground mode of the cavity. And I'm writing now the rate equations, because for pedagogical reasons, it's easier if we talk about single mode cavity. Now I assign each process a letter, so pumping gamma up, leakage kappa, spontaneous emission gamma down, and alpha here corresponds to absorption, the molecule from the cavity mode, and epsilon is the emission. For example, for those two green processes, we can write down two equations. One is for photon number n, and one is for excited molecule number nb. And these are the terms, and they are exactly opposite of each other. They are basically Einstein rate equations. So if we lose a photon, we gain excited molecule. If we lose excited molecule, we gain a photon. So they are kind of lossless processes. And now the red ones, I add photon leakage here, spontaneous emission here, corresponding proportional to excited molecule number, and this is pumping, corresponding proportional to the ground of the molecules. And for pedagogical reasons, I'm going to show you that these rate equations lead to a Bose-Einstein distribution. That the photon, yes.
rate equations, like they only involve population, right?
No, these are mean field, yes.
Is this just right?
Yes, because we lose coherencies when we have large molecule number and large photon numbers. And photon numbers, critical photon number in the cavity is around 80,000. And molecule number is around 1 billion. if you talk about initial time dynamics when you start pumping the molecules, maybe then yes, there is some coherence, but they are quickly lost in the steady state, definitely. Okay, so I'm solving those guys now, and what I'm taking is the steady state. I'm taking that those guys now don't change in time, and I can solve algebraically, it's very simple. And I get n bar, so n bar now corresponds to a steady state. I get alpha over epsilon and mg over me, but again, that's not the steady state. But this is definitely not a Bose-Einstein distribution yet, although you see some similarities. I'm going to do some further assumptions. First, I'm going to assume that epsilon over alpha is this Boltzmann factor. And then I'm going to define mu, chemical potential, to be this guy. And what I'm getting now...
I'm sorry. So consider that mechanism where you start the photons from one mode to another, what they have, so without changing the molecular population.
Yes, I mean, in this case, I only assume single mode. In general, you have more modes.
Right. So the only mechanism for leakage is just leakage from the camera. You are not scattering to other nodes.
No, they can be scattered to other modes. It's just that now I don't consider them.
That's right.
Yeah. And okay, so now you get this guy, and this is definitely a Bose-Einstein distribution. Now, okay, maybe people will agree that we can define this guy. This guy is somewhat tricky. Why this should be true? I'm going to talk about this in the next slide. But now I want to also give you attention that it's funny that chemical potential is actually determined by the molecule number. So if you don't have any excited molecules, there is no condensation. And when excited molecule number reaches half of the total population, then chemical potential goes to zero. And we achieve the condensation.
So epsilon and alpha, just to make clear, are like the gap into the ground and excited state of the molecule.
Epsilon is emission of the molecule in the cavity mode, and alpha is absorption from the cavity mode in the molecule.
Picture.
Now I'm going to show you more in detail how those photons are absorbed from the molecules and what we are doing actually in the experiment. Also about this guy. So what I'm showing now here is the molecule which we are using in experiments. It's called rhodamine 6G, which is also used in dye lasers. Here you see absorption spectrum and emission spectrum. These vertical lines are the cavity modes which are crossing those particular frequencies of emission spectrum. And here we are pumping the molecules far away from cavity modes at 532 nanometers. So the only way photons can enter the cavity modes is via the molecules. So there is no direct rejection of the photons. And that's why we can also describe these things with rate equations. You don't need any Hamiltonians or these things. And now this, which I showed before, it's called Kenner-Stepanov relation, and for this type of molecule, this is true. So particularly here I'm showing epsilon over alpha, which is just ground mode. This emission coefficient here divided by absorption coefficient here corresponds to this one. The frequency here is the frequency difference between this crossing and this ground mode. And in general, this is true, which means that molecules are thermally distributed. Not every molecule has this property, but most of them have. And that's why we can, because of this reason, solely because of this reason, we can get a condensate in the photons, basically. Or thermalization, rather.
Sorry, there are symbols in connection.
So this one, yes, you can, I've never derived it, but you can consider molecules as dressed two-level system. So you have electronically two levels, and each of those levels are dressed with raw vibrational states. Raw vibrational states, so phononic degrees of freedom. And then you start calculating probabilities of exchange of those states, and then you get to Boltzmann distribution, basically. I don't remember the details, but you can do this with some statistical mechanics. Okay, so I mean, this is basically the end of my introduction. If you still have any questions, otherwise I will go to the project.
People motivated in utilizing this, experiment?
Well, it's actually interesting because, first of all, it's like a textbook scenario, almost ideal gas, because you can do very nice experiments with this. Also, if one of the more practical maybe reasons could be some new type of light sources. Right now they try to create VUV light source with this one. Because VUV, we don't have light sources of VUV lasers. And with condensates it might be possible, although that's a long shot so far. And in general also the fact that this is not just photon system, but it's a molecule coupled with photons. It's a very rich environment to study. And yeah, there's a bunch of stuff which still is not explored. And this thing is also highly nonlinear. Like if you go to some stronger cases, which I will talk about in the next slides, you can get some nonlinearities in time. And, yeah, I could talk a whole presentation about why it's interesting, but these are the main reasons. Yes, okay, so now I'm going to talk about this project, Driven-Dissipative Photon DC. And so the idea was that before what I showed you is you have a cavity and we just pump molecules constantly with a constant pump. And above certain threshold of critical photon number, we observe the occupation of the ground mode. And this is all in steady state, so no time dynamics involved. Now, what we would like to do here is to investigate the properties of condensate in time. And how we would do this, instead of constantly pumping the molecules, we would pump them with an oscillatory intensity. So a sinusoidally oscillating intensity. And we would like to see how the condensate responds in time. So if we would drive the condensate with different frequencies, we would like to see how the condensate responds to those different driving frequencies, with what amplitudes. So that's the idea, and now I'm going to show you. First, I will start with theory, because then it's easy to understand what's happening in the experiment. Okay, so we are back again with the old good rate equations, which I already introduced you before, but only now we have additional term for the molecules. We are now driving molecules with constant gamma, and on top of that, we have some oscillation amplitude R0 and frequency omega. So this is sinusoidal driving term. And I would like to solve those equations now in time. Or rather, I would like to obtain a single equation just for photons in the limit of weak driving when R0 is small. Now, so what do we do? We can assume that N and NE of T can be separated in two solutions. One is N bar, so steady state, corresponding to this pumping, and oscillatory N tilde, corresponding to this one. And now this oscillatory, we can assume a solution and 0 times sinusoidal function. So N0 is the amplitude of the response. And we assume that in general, we expect condensate to oscillate with the same frequency with which we are driving. And also we expect to have some phase accumulation phi. And the same for excited molecule number. But here they will assume different phase in general. Now we plug those guys in the rate equations, and we utilize the fact that this guy is 0. And we also throw away all the higher order terms in tilde. So any tilde times n tilde, we drop away, and the same with mg tilde n tilde, which means that we are looking at the driving amplitudes which are small. Now, what we find is we do those juggling with equations. We find single mode equation, a single equation for photon number, oscillating photon number, which is found in the second order of time differential. And probably most of you already see that this is actually an equation which describes driven-damped harmonic oscillator. Now, might be simple, might be too trivial, but actually it's not trivial because here, so big gamma is the damping term, omega 0 is the pre-oscillation frequency, and this is the curve. Each one of them corresponds to all parameters of the condensate, basically. Here, n bar, the average photon number, or the steady state photon number, and n here is the total molecule number, and also those alpha, epsilon, and gamma down parameters. Now, here that I have highlighted is that we will drive, in experiment, we will drive different frequencies, but we will also change the steady state photon number and see how the condensate depends on that. So this is what we will control in the experiment, and what we can measure in experiment using this method will be the total molecule number and cavity decay, because that in general we don't know. Now we can solve this equation, this solution. So this is absolute value of the response amplitude. And here, these guys are now explicitly written, and don't worry too much about, they actually are not that complicated. This bracket is always there. And interesting fact is that omega is multiplied by gamma down, while for gamma, these gamma down is added. So it will give some interesting scenarios, which I will show you later. Now, that's basically the theory, and this is enough to describe driven-damped condensate. Now, let me go to experiment and quickly talk about what I did to implement this oscillating intensity laser. Because if you have output of the laser, of course, it's constant intensity. And what I utilized was a beating effect. Don't worry too much about details, but what happens here, this is an interferometer. This is initial light coming in, and then this part goes here, and it has a frequency big omega corresponding to 532 nanometers, so green light. And now here in this part, I have another beam coming, and this part creates, or let's say shifts the original frequency by middle omega. So it comes here through acoustic modulator, passes back again, and now it comes here. Now this initially had omega, this guy now has omega plus small omega frequency. And what happens when we overlap them, when the frequency difference is very small, we will get a beating in intensity, like basically from classical mechanics. And we overlap them, and then this is now the intensity of our laser. And this then we direct to the cavity. Now, how the cavity looks like, partly answering to your question, this is maybe the scale, is that this is just a screw, and this is a simple mirror holder. So the cavity is very small. So these are the mirrors, and in the middle there is a liquid dye solution, which has, the dye solution is rhodamine 6G molecules dissolved in some alcohol. Here, from this side, we pump the laser, and then from the mirror sides, because mirrors still are leaky, we have the condensate emission, and this emission we use to record data. Now, this is the full experimental setup. Don't worry, I'm not going to go into the details. just to see how it looks like.
In this project, you did more calculations than expected.
Yeah, both of them, yes. But I didn't, the only part which I implemented was this rectangle. So outside the rectangle, this was already there. And I implemented this beating effect setup here. As you see, the green is the unmodulated laser. Then it goes into this system, this interferometer, and this purple light now is the modulated intensity, and then it goes in the cavity. And then the leakage, the leaky condensate with the orange is used for recording stuff, camera stabilization, and also for the time traces. Yes. Also, yes, okay, that's enough. So how we did the experiment, we were sending pulses of the laser. So oscillating, so don't worry about that, we just had pulses. So no laser, laser, then again no laser, laser, for around 600 nanoseconds length, and then we waited 20 milliseconds, and we used those pulses to avoid some certain unwanted effects in the molecules, so they can relax back during those 20 milliseconds. And how the single pulse looks like, this. Okay, this is something weird. But so this is just the pulse, which we actually measured. So the red is the laser signal in the photodetector, and the blue one is the actual condensate signal. So this is the photon number in the ground mode. And what we did at the first part of the pulse, we didn't oscillate, and then second part of the pulse, we turned on the setup trace down, and then we had oscillations in the laser, and also correspondingly oscillations in the condensate. But now this is actually, it's averaged. It's averaged over hundreds of time traces, because if you take single time trace, the condensate is very, very noisy, and we cannot see it. And basically, this is the amplitude which we will fit and we will measure. And now going to the actual results. Again, I'm showing some time traces, but now I'm showing parts of it. It's a part of a pulse, which is oscillating. And here now what you see is the condensate in the blue for two different driving frequencies. So 100 megahertz and 240 megahertz. And the red one is the laser. And what we first see is that the condensate indeed oscillates with the same frequency as the laser, both in all cases basically. And what we also see that for higher driving frequencies, the phase becomes larger, phase difference, which is consistent with the driven-dissipative harmonic oscillator theory. And the lines, the solid lines are the fits. So the blue solid line is the sinusoidal fit of the solution, which I showed you in the theoretical part. And this is the time in nanoseconds, so you see it's corresponding to those frequencies.
So those peaking parameters are the ones that you said are measured in experiments, or like you had the blue one and green ones in the formula?
Yes, yes.
Which of them is the...
I'm not yet fitting anything. I'm just fitting. No, I'm fitting only N0. So I'm fitting just the photon amplitude. And if we go back, so I'm fitting this guy now. And if I know this one, and I know a bunch of other parameters, I will be able to extract an E and kappa. But I will show you later how I extracted those. So basically now what I'm doing, the procedure now of the experiment is like follows. We drive the condensate for different frequencies, and also on top of that, we drive the condensate for different photon numbers. So let's say we have 1,000 photons in the system, we drive them for the whole frequency span. Then we go to 5,000 photons. Again, we drive in the whole frequency span. And then each time we record the photon response amplitude.
This response, what does mean that I should discard any other explanation for this behavior?
The thing that you can make sure that this is a condensate is, remember the spectrum in the first slide, which I showed? That's basically, we have another monitor which we see, okay, this guy is in a condensate, and we can, from that spectrum, we can feed the photon number.
But that spectrum was the same.
Yes, but but the spectrometer, it's very slow, and it averages over. So what it's recording is what you see here. So for example, this is oscillating, but the spectrometer will record that it's around 10,000 photons. So it will record this one, the middle part, the mean value. And this is basically the mean value here is basically this n bar, which is, we call it steady state, or maybe more correct way to be calling it averaged photon number. And from here, you cannot see that this is a condensate. You still need to look at the spectrum, and yeah. But what we do is that to record this signal in the experiment, we filter out all the excited modes. So we are only looking at the ground mode. Okay, so now what you see here is exactly what I told you. So we scanned our driving frequency from 60 to 320 megahertz for average photon number from 1,000 to 12,000. And the dots are experimental values, and the solid lines are the fits, and these fits are from the solution of driven-damped harmonic oscillator. As you see, it's matching quite well. For example, here also, this guy saturates, which is, okay, don't worry about that. Okay. What you need to worry about is that for low photon numbers, the maximum of the peak is at zero frequency, those two cases. But then, here, the maximum disappears at zero, and it happens at finite frequency. And for increasing photon numbers, the speed goes to the right. Which means that our free oscillation frequency increases when we increase the average photon number in the ground state. And also, not only the frequency, but also the width of these changes. Right? And as you see here, it's some criticality happening because here the system is in overdamped region, and because of the peak emergence in these cases, the condensate undergoes the underdamped solution, underdamped oscillations. And this transition from underdamped to overdamped could be called like a non-Hermitian phase transition in photon numbers. It's not like a non-Hermitian transition in Hamiltonian, but in particle number. And if we now extract the big gamma, so the damping and the free oscillation frequency from those speeds, we can plot another one, so directly to show how those parameters depend on the photon number and bar. This is free oscillation frequency, this is damping. Dots are experiments, solid lines are theory. And as you see, it's matching very well, both cases. What I wanted to show here also, I plotted a dashed line. So dashed lines here are from theory, assuming there is no spontaneous decay of molecules. And what you'll see is that this assumption holds well for high photon numbers, but for low photon numbers, it goes down, while spontaneous decay really plays large role for low photon numbers. And this is also, if you remember, I said that free oscillation frequency is multiplied by gamma down. Damping is just added by gamma down. And this is what you see. This is a multiplication effect. This is just adding. It's like a constant also. Now, knowing those guys, this particular dependency, we can find, from those fits, we can find the parameters of cavity decay and total molecular number, because other parameters like absorption and emission coefficients, we know from molecular spectrum. So you see, this is around 7 gigahertz, and molecular number is around 4 billion molecules in the cavity. And yes, the main message is here that BC dynamics depends on the particle number, and not only the dynamics itself, but also in what way it oscillates, either it's underdamped or overdamped.
And this value of kappa, how does it compare with, I don't know, radar measurements?
Sorry, with what?
So kappa can be also from other ways, going other ways, like radar.
You could probe, I guess, yes.
But say you didn't compare this thing to kappa.
No. Yes. Okay. Now I think I'm done in terms of experiment, but I was interested in general to see further what happens, because here we change photon number and we can go in underdamped or overdamped regime. I wanted to see what happens if we change not only the average photon number, but for example, we change kappa, or we change the total molecule number. And I wanted to plot a phase diagram, and I'm going to show you numerical calculations which I did. What I'm showing here is now a phase diagram of the condensate. And the red parts are when the condensate is in overdamped regime, and blue ones when it's in underdamped regime. And just to familiarize yourself, the experiment that we did was for those vertical lines. So for gamma down corresponding to this vertical line, and for kappa, we found the fitted value. This is the fitted value in the experiment. And we scanned photons in this shaded region. As you see, if we have fixed kappa, which has photon number, then here around 2,000 photons, it goes into underdamped regime. So this is a particular experiment. But now I wanted to see what happens if we change also kappa and gamma down. And in general, what you see for kappa, increasing kappa, we tend to go into the overdamped regime. But what is particularly interesting was this cusp point for changing gamma down, which to be honest, I haven't really much analyzed. We just observed this, and it seems that there could be some type of criticality, because it's completely different than. I mean, it's very sharp. Those guys all are kind of. So yes, it could be interesting also to see experimentally what happens, but the problem would be that we need to do gamma down experiment for kappa, which is not that easy to do. So, yeah, I think that those are basically the conclusions. First, I showed you that the photons can thermalize and they can undergo a Bose-Einstein condensate. Then, secondly, I showed you that in limit of weakly driven photon gas, we can describe the photon oscillations as driven-damped harmonic oscillator. And finally, I showed you some experiment. And in particular case, I showed that VC dynamics depends on the condensate size, or in other words, of the particle number in the ground mode. So, yes, as Francesco mentioned, I was so this is my Freiburg group where I was physically located. This is my professor's group, but he was in Kassel, so we worked remotely. And this was the group where I did my experiment. So thank you very much.
I'm interested in the overlap potential. I kind of have the intuition that for two small numbers of what set the galaxy and too high dumping, and this is now overdumping energy. It makes sense. But you also had overdumping power for a number of photons in the galaxy and still relatively low dumping. The part on the right. What's your intuition why we should
In overdamped regime in which limit?
on the right, like I
Here.
kind of have an intuition on the last part, but
Okay.
it's very small.
Yeah.
But on the right, I have a very large equation of that, and still small. Okay.
Yeah. So basically, these regions.
Yeah.
To be honest, could be that because these numbers are quite huge, it's like million photons, and this could be already starting to be comparable with the molecule number in the cavity. So maybe because they somewhat become similar, there could be some explanation. To be honest, I haven't thought about it. I have an intuition why we always end up in underdamped region when we have high kappa. That's maybe I could explain this one. Because imagine if you have very high cavity decay, if you excite molecule, then the photon which gets emitted, lots of them get quickly lost. But then you need to reset your let's say stable regime, and it quickly goes back up. Because if you have lost photons, it needs to return to your, let's say, stable position. But then it overshoots, and then you again have a leakage, and then it again goes down. So it has these oscillations. If you have kappa, which is small, then you emit the photon, and it's not lost. So there is no overshooting over the stable state. Something like that. And maybe you could reason somewhere for this region, but I cannot answer that. Yeah?
I have two questions. So the first one is the very first slide you show that people back in the days doing ECU atoms. Then now people do photons. Recently, some groups that also done ECU molecules. It's like a step forward from atoms molecules.
Yeah.
So from the photons point of view, is that like someone who on that, or it's like they release the photon and say they nothing more to do. And that's the second question. So I just know I'm not an expert in ecology, but there are people doing like one of the network physics with the how the weeks is. And I was wondering if there is something is there other physics, with the core physics and stuff.
Okay. Yeah. So first question. Yes, molecules. Between photon and atom condensates in 2006 or 7, there was a first condensate of exciton polaritons, for example, or condensates of magnons, or a bunch of these guys. Photons, I think, came actually one of the latest ones. I'm not sure. One of the ways you could additionally create a condensate which was a recent paper, was instead of molecules, you would do it in a solid state, which would make actually life easier. If you have solid state, you could actually implement this technologically later. But other type of bosons, I don't know. It's hard to tell because if you maybe want to see a condensate of elementary particles in standard model, I don't know, might not be possible. It's I haven't really thought about it. Condensation of Higgs boson. I don't know. But yeah, and other than that, what you said, the second one, yes, there is a bunch of stuff happening in atom condensates, which try to simulate analog black holes in waveguides or stuff. And actually, these are some of my suggestions in my thesis outlook to do exactly the same with photons. And there was even one paper which suggested, it was a theoretical paper which suggested how you could simulate black hole in photon condensate, which was very stupid. You just drill a hole in the mirror and then you introduce infinite leakage. And they calculated some theoretical stuff, and yes, there should be some experimental implementation of this, which sounds definitely something interesting. But yes, I think with photons you could do it. And also I think it would give you some maybe benefits, because one of the benefits in condensates is you can easily control particle number, which you cannot do in, let's say you can tune chemical potential, like by just tuning laser. In atom condensates, you cannot really do that.
And effective mass, no? So you can play with effective
Exactly.
mass.
Yes, you can play with effective mass, but you can.
Just not the yes.
I forgot also about, I didn't mention it like here, but you can also do, you can tune cavity modes to go to different regimes to the spectrum. And this is actually how fluctuation dissipation theorem is proved in condensate with respect to the response of these guys. And I forgot that in our, let's say, long time dream with the driven condensate would be to prove frequency dependent fluctuation dissipation theorem, which is something which we cannot do yet.
Do you gain any advantage to have EIT regimes instead of having say two-level molecules, you have three-level ones, you use Raman transitions and go to transparency regimes. So you play with the epsilon and alpha, for instance.
No, I mean, I don't see how playing these guys will introduce you to a three-level system, because those two peaks come from two-level system. This is for one electronic level, and this is for another electronic level. So you need to have a different molecule then, I think. Or, I don't know, maybe you need to have more spectral resolution to get more peaks.
No, I'm referring to